Good morning. Good morning. Good morning. Adam, kindly pray before we start our lesson. Allah,
Hello? Hello?
Adam. No one is willing to pray. Denzel.
Let us bow our heads for the prayer. Heavenly Father, we come before you saying thank you for the gift of life, saying thank you for the protection and guidance that you give us all the night. We do pray that as we go to study this physics lesson, we do pray that you send the Holy Spirit upon us, that we're able to understand whatever we're being taught today, Father, and may be with us and guide us all this day. We pray this, trusting and believing in Jesus' name we pray.
Thank you very much. So today we are going to do magnetic effect of an electric current, and you can see the screen. Kindly confirm that I'm clear to through the chat session. Thank you. So in this topic, we are going to see quite a number of rules. And the rules will help us to answer all the questions in this topic. We have the ampere rule. We also have
Mr. Rob.
Yes.
Can can you have two devices? That's why we have echo. So
Okay. A minute. So by the end of this topic, magnetic effect of an electric current, we should be able to answer the following questions, or you should be able to know the following in this topic. This topic is more of theoretical and practical and more of experiments and demonstrations. So by the end of this topic, you should be able to state rules related to this topic. That is we have the first rule, Ampere's rule. We also have Ampere swimming rule. We have the Fleming's right hand grip rule. Fleming's right hand grip rule. Fleming's we have also the Maxwell rule. So we'll we'll use these rules to answer the questions, especially on the diagrams. We begin with the first one, Ampere's rule, Ampere's swimming rule. So we said you must first know the rule for us to answer the questions. So it says that if one imagines swimming alone, if one imagines swimming along a conductor in the direction of electric current and facing the compass needle, then the north pole of the needle will be deflected towards the swimmer's left hand. So we consider someone swimming, then we also consider the position of the left hand, So in swimming, those who are in the swimming, who normally swim, we have the types of swimming. So while swimming, either backstroke or any other, you must consider the position of the left hand, and the position of the left hand will show the direction of deflection. Let us begin from this diagram. Yeah. Can we consider this person who is swimming? We have the normal swimming and we have the backstroke. And in both cases, we have said, while using the Ampere swimming rule, we must consider the position of the left hand, and that will be the direction, the north pole of the compass. So the first case A, for the first case A, you can see the compass now, and you can now see the position of the, you can see the position of the conductor, whereby the conductor for this case is the one carrying the current. And for normal swimming, this one is added to the top. The first one, case A, this one, the person is swimming towards the upward position, this one, and this is the left hand of this person, meaning this one will be the north pole. So we are using the rule to determine the north pole of this compass. In B, the person is swimming towards the this direction, meaning ameturn, alikuwa anaenda this side at first, sahi sasa amerudi this other side downwards. We will also consider the direction, the position of the left hand, and that left hand position will help us know the north pole. So this will be the north pole for this case. For backstroke, meaning backstroke, the conductor is above the person here. The conductor is here. Now consider the position of the left hand. You see the person is facing upwards in backstroke. The person is facing upwards in backstroke, and the position of the R. So any question related to Ampere's rule, you will use this concept of using the swimmer's left turn, and you should also know the direction of movement of this conductor. You should first see the direction of the conductor, then you see the position of the left turn of the swimmer. So for this case C, the north pole will be on this left-hand side. That is same to case D. Same to case D during backstroke swimming. This is the same concept. This is the position, the direction. This is the direction of current. This is the direction of current, and the compass. The compass for this case is under the wire. The first case, there is no current. There is no current, so that one is neutral. Case B, compass is under the wire. The compass is under the wire. So if you imagine swimming in this direction, you will notice that your left hand, the swimmer's left hand will be this other side, and that side will be the North Pole. For this, the compass is over the wire. Case C, the compass is over the wire. Will the swimmer swim normally, or the swimmer will use backstroke method? Someone to try that. For case C, will the swimmer swim normally or use backstroke backstroke swimming method? Victor?
Backstroke.
Yes. So for it to be easier, you must demonstrate. You must also imagine swimming. You can even use something like there's a talk hapo nje utumie miti ama anything straight, and then you change the direction of current flow. So for this case, the current is moving upwards, and when you use backstroke, meaning your left-hand side will be in this other position, and your right-hand side will be in this other. So there are two possibilities. Wakati una swim ukiangalia chini, either the left hand iko hii side ama the right hand iko hii side. Ukichange kwa backstroke, the left hand will be in the opposite direction. That is how the Ampere's rule is working. Then we go to this magnetic field, patterns on a straight current carrying conductor, magnetic field patterns on a straight line, on a straight current carrying conductor. For this case, we also must consider the direction of current. We must consider the direction of current, and we are normally guided by this terminal here to know the flow of current. So the flow of current will start from this point to this other point. So from Fleming's Fleming's right-hand grip rule for current carrying straight conductor, Enos, you have something to? I see Enos, you are raising your hand. Do you have an additional clarification or a question? Disappeared. So we continue. So Fleming's right-hand grip rule for current carrying straight conductor, it states that if a current carrying conductor is along the wire in the direction of current, the other fingers will point in the same direction of the magnetic current, of the magnetic field. So for this right-hand grip rule, we must, we must consider the direction of current. For this case, we are considering a current on a straight conductor, current on a straight conductor. So we have already mentioned that if a current in the right-hand grip rule, if a current carrying conductor is gripped in the right hand with a thumb, can we now use our pen facing in the upward direction? Let your pen be the conductor for this case, and the current is moving upwards. So the thumb will be pointing direction of current. Can you use a conductor to be a conductor? Use a pen to be your conductor and grip that pen. So the thumb will show the direction of current, and these other fingers, these four other fingers will point in the direction of the magnetic field. That is why you can see the direction of magnetic field moving in the anti-clockwise direction. The case will be different if we change the direction of, now can we change, our conductor was facing upwards, can we now interchange such that our conductor faces downwards, meaning you will twist your hand to face downwards. Then you give us the direction of the magnetic field. This one, the current is facing upwards, and what is guiding us to know that the current is facing upwards is the thumb of this right hand. If you use the left hand, you will fail. You will fail because the rule for this case is the right hand grip rule. So what will happen if we interchange this direction? Tulikuwa tumeshika ione juu, tushike sasa in the opposite direction, meaning we turn this, the thumb will face downwards. The thumb will face downwards. What would be the observation in the magnetic field? Will be the direction in the magnetic field. Arnold?
Clockwise.
Clockwise direction. Yes, clockwise direction. This one is an anti-clockwise. So in order to say whether the direction is clockwise or anti-clockwise, you just use the clock. I hope there is none facing difficulties in determining whether the field is headed in the magnetic in the clockwise direction or not, or anti-clockwise direction. So for this case, this is clockwise. When we change the direction of the thumb to face downwards, it will move in the clockwise direction. Consider this. The current will flow from this point to this point, meaning as you use the rule, hapa ndio utakuja hapa ndio itakusaidia. So try to, you normally use your pen. Your pen is very efficient for this case, especially in this topic. Your pen can, or any other straight object here. So you grip this conductor. The thumb will be pointing the south direction huko chini, and your fingers, venye fingers tu inaenda hivyo ndio itakuwa the direction of magnetic field. Magnetic field patterns due to current carrying a circular loop. Can we consider this position? You can be given this diagram, then you are told to show the fields. If the current is moving upwards here, let's first this was for straight. So such a question you can be asked to show can be asked to show the magnetic field pattern inside the loop. Show the magnetic field pattern inside the loop. Of course, you'll be given the direction of current here, meaning if this is the direction of current, the current will be flowing through this conductor this way. By the time it reaches this position, the direction of current will be facing downwards here, be facing the south. So consider this point and use the right-hand grip rule. For this case, you can use the diagram. Instead of using the pen for this case, using the diagram is also possible because you can see the direction of current. So for Fleming's right-hand grip rule for a current carrying, for example, in a solenoid, let us start from this, then we answer that other question there. This is a solenoid, long cylindrical coil with many connected loops. That is a solenoid refers to a wire wound into a long cylindrical coil with many connected loops. So for this case, we'll also use the Fleming's right-hand grip rule for a current carrying the solenoid. It can be used to predict the direction of magnetic field pattern inside the solenoid due to the current. Because in every case here, we must know the direction of current. In other instances, the direction of current is given, then we apply the rule. So if a coil, for this case, of a magnetic field on a current carrying the solenoid, if a coil carrying electric current is held in the right hand, such that the fingers encircle the loops. So for this case, the fingers will encircle the loops while while pointing in the direction. The loops will have the direction of current. So the current is moving to this downwards here from down. So if we use this rule, I want a straight line. The first case was for a straight line, but this one is the magnetic field on a current carrying the solenoid. And we have already known that the solenoid refers to a wire wound into a long cylindrical coil with many connected loops. So those loops will have the direction of current from a current source. Then, can we now use the rule to determine the direction of the North Pole? And if one side is the North Pole, it means the other side of it, the opposite side, will be the South Pole. The rule states that if a coil carrying electric current is held in the right hand, such that the fingers are encircled, such that the fingers encircle the loops while pointing in the direction of current flow. I want us to consider this. So the loops, the direction of current is flowing from this point to this point in every loop, in the loop here. So this is the direction of current. So we will make sure that the fingers encircle the loops. But the fingers also must point the direction of current flow. Meaning, those fingers should accompany the loops in the direction of current. Now, from this diagram, where will the North Pole be? What is the position of the North Pole? Say that the current is flowing from in this direction. The current is flowing in this direction. Where will we get the North Pole? From that diagram. In this diagram, the North Pole. Larry?
On the right-hand side.
On the right-hand side. Thank you. So you have noticed that if you are in a position to know the rule, if you know the rule, there will be no difficult question if you know the rule. So make sure you know the rule. Another very important concept, the magnetic field patterns on the straits the magnetic field patterns on a straight current carrying conductor. The two symbols are very important. This first symbol of X and this other one of a dot. It is very easy to forget these symbols, this one and this one. One of them will indicate that the current is flowing upwards. The other one indicates that the current is flowing downwards, or in simple terms, the current is flowing into the surface or out of the surface. So this one, the current is flowing into the surface. Into the surface. This one, the current is flowing out of the surface. So if you are given these two symbols, you'll be given one, this one and this one without the magnetic fields. without these magnetic fields. Now it will be upon you to show the direction of magnetic field. You will be given this one, this symbol, and this symbol the way it is, and you are told to indicate the direction of magnetic field. So if this one means that the current is flowing into the surface, meaning the current inateremka chini, and that this one is upward current. The current is originating from this dot, which is a symbol of upward current. So the current is flowing upwards. The current will be flowing upwards. So we'll also use the rule. Which rule will we consider to know the direction of magnetic field? Which rule will we consider to show the direction of magnetic field? Which is the most appropriate rule? So far, so good. For us to know the direction of magnetic field. Francis Mungai. Francis Mungai.
Fleming's right-hand grip rule.
Yes. So I want us to change this. I want us to change this such that both of them can we use these two symbols at a distance like 5 centimeters away. Let us use this downward current, and tutumie hizi mbili, this one. Let us use the symbol of downward current and two of them at a distance of around 5 or 6 centimeters away. Then we indicate the direction of magnetic field. Then we indicate the direction of magnetic field. Then you give me the direction of magnetic field in the first, on the left side, and the direction of magnetic field on the right side. If we are using the symbol X, current down. Saying instead of using current down and an upward current, we use both cases to be downward current and here downward current. Then you give me the direction of magnetic field in both cases. What would be the direction on the right side and on the left side? Of magnetic field? So if you have known how you can, sorry, if you have known how you can determine the direction of magnetic field using the current down and current up, you can be able to relate when it is both the representation of current into the surface. I'll show you some example questions towards the end of the lesson. You have this other rule of you have the motor rule. You have the motor rule. Can be told to state the motor rule. State the motor rule. Another important rule to know. Another important rule to know. We began with the rules, then we go to factors that can. Then we go to factors. So Fleming's left-hand rule states that if the thumb, the first and the second fingers are held mutually at right angles, with the first finger pointing in the direction of magnetic field, the second finger in the direction of current, and the thumb points in the direction of force. But this is now Fleming's left-hand rule. Sometimes I used to see that some of you, instead of using the left hand, they use the right hand. Don't know where the confusion was coming from, or where the confusion is coming from, but in Fleming's left-hand rule, we must use the left-hand rule. Fleming's left-hand rule, we must use the left-hand rule. And you must know the position of those, the first finger, this is the first finger showing the direction of, the first finger is showing the direction of, pointing the direction of magnetic field. The second finger is pointing the direction of current, and the thumb is pointing the direction of force or motion, direction of force. So you realize that in this topic, we are just using the rules and either the left hand or the right hand. For this case, the Fleming's left hand rule. It is important first, before you begin anything, you know the rule, then you know the position of, you know that the first finger is the magnetic field, it points the direction of magnetic field. The second finger will point the direction of current, and the thumb will point the direction of force or motion. So in a question or in an experiment, you will be given, you can be given the magnet with direction the North Pole and the South Pole, meaning you can use the finger to determine the direction of the north. Magnetic fields normally begin from the north to south. They always begin from they always originate from the north pole to the south pole. So if you are given a diagram with two magnets, north pole and south pole, you fix the finger to point the direction from the north to south. You can also be given the direction of current. Then you are asked to show the direction of force. So in Fleming's left-hand rule, you'll be given two. You'll be given two. For example, the direction of force and the current, or you can be given the direction of current and the direction of magnetic field. Then you determine or you show the direction of force. Here is an example question. So for this case, we have the magnet, we have the North Pole here, and we have this is the bar magnet, the North Pole and the South Pole. This is the direction of current, and the direction of current here is not the direction of current in this side. The direction of current here is different from the direction of current in this other side. We can use this to know the direction of force, meaning we can begin from, we are using the Fleming's left-hand rule. We are using the Fleming's left-hand rule. And we have already been given the North Pole and the South Pole. And we know the magnetic fields originate from the North Pole to the South Pole. So the first finger which is pointing the direction of magnetic field will point this direction, and they should be mutually held at right angles, meaning the three fingers should be 90 degrees. They should be perpendicular to each other. So the first finger will be pointing towards the South Pole. The first finger will be pointing towards the South Pole. We are considering this point AB. We are considering conductor in AB. And the current is flowing in this direction from B to A. So the current and the force will automatically, the thumb will automatically point upwards, and that will be the force, meaning you must know the representation of the first finger, the second finger, and the thumb for you to answer this question. When we consider this other position, you know, the current is originating from this. Maybe we have a power source somewhere here. A power source is not indicated. So the current is flowing from D to C to B to A. So when we consider this, the point DC, the magnetic field direction is still the same. The first finger will point towards the right side. The first finger will point towards the right side. Now you will twist the second finger. The first finger will be pointing. You twist the finger such that the magnetic magnetic field is originating from the north to south, then you twist the other finger such that the current is flowing in this other direction. Then it will give you the thumb, the position of the thumb will give you the direction of force. Can you try this? This one was simple. This one was direct, because if you use the first, if you use the rule, the second finger is pointing towards you. The second finger is pointing towards you. The first finger is pointing to this other direction, and the fourth is pointing upwards. The thumb is pointing upwards, and you must after you must use a ruler here, and it should originate from this conductor here. Then you indicate the arrow, then you label force so that we know that it is force. Now, these other, I want to know how you will twist your left hand. You'll use the rule to twist the left hand here, such that the direction of force will point downwards. Someone to try that? Someone to try that? How will you determine the direction of force from D to C? How will you determine the direction of force from D to C? Any trial? The second finger will, in this first case, the finger was pointing towards you. In this second part, the finger should point it was pointing towards you. So the second finger will point the opposite side. For the first case, the first finger was pointing towards you. So in this, from point D to C, it will be pointing the other direction, towards this direction, from D to the other direction, the opposite direction. If the finger of, if the current, if the finger, the second finger is pointing the direction of current here, from this point to the other direction, the first finger will automatically point the direction, the north-south direction, and you will realize that the thumb will point downwards. Can you confirm if you are someone who have used the left-hand rule here, and has been able to find that the force is facing this direction, anyone who was able to get the direction pointing downwards, direction of force, or anybody with challenges, this one you must demonstrate. Give you another question. This is an example question. Consider this question number 17. An insulated copper conductor XY is the conductor, lies over the fixed wire connected to the battery, this one. So meaning the current will be originating from this point towards this other point. So this one will help you. This one will help you to determine the direction of current. So the current will be flowing from this point, going upwards to this other point, meaning reaching this side. We consider the current. We consider the current here. We consider the direction of current in the conductor here. We already have the magnetic. We'll get the magnetic field, the direction of magnetic field, because we have the magnet and we have current. So we'll be asked to determine the direction of force. Let us begin from question 1. State and explain the observation, meaning state is the first mark, stating is the first mark, explaining is the second mark. State and explain the observation made on the conductor XY when the switch is closed. When the switch is closed. Question number 17. Question number 17. An insulated copper conductor XY. An insulated copper conductor XY lies over the fixed wire connected to this one. State and explain the observation made on the conductor XY when the switch is closed. So for the first case, here, for the first question, the current will flow along XY. The current will flow along XY. We said this where the battery gives us the direction of current flow, so that the flow will be moving from this point to this other point. So the flow of current will be along X, Y, and not, it will not be YX, it will be XY. And the conductor rolls along the fixed wire towards the support. Or the conductor will roll towards the fixed supports here. So the first mark is stating where the current is flowing to along, and the second one is the movement, the motion. The conductor will roll along the fixed wires, or it will move towards the supports, the fixed the supports. In which direction does the wire XY experience force? We use Fleming's left-hand rule. We'll use Fleming's left-hand rule. And from Fleming's left-hand rule, we already have the magnetic field direction from this north and south. So the first finger will point downwards. Then we consider the direction of current. We have already said that the current will be flowing along XY. The current will be flowing along XY, meaning the second finger will be pointing towards U or towards Y. The second finger will be pointing towards Y. The first finger will be pointing downwards. The first finger is pointing downwards. The second finger is pointing towards Y, meaning as you demonstrate, it is pointing towards you. Then the thumb will point the direction of motion of force automatically. So the direction of force will be from this conductor towards the right. So the direction of motion will be to the right, How do you determine the direction in one? We have already used Fleming's left-hand rule when the hands are mutually held at right angles. When the force on the wire, when is the force on the wire greatest? It is greatest when the angle between the conductor and the field is 90, are mutually at right angles. When the angle between the conductor and the magnetic field is 90 degrees. What will be the effect of reversing the effect of reversing both the magnetic field and direction of flow of current? The effect of reversing both the magnetic field, meaning we are interchanging. The south pole will be in the upward position, and the north pole will be in the downward position here. We are also reversing the direction of current flow, meaning in the first case, the current was flowing along XY. We are now changing the current to flow from Y to X, meaning we'll change the terminals here. If you want the current to flow from Y to X, we are changing the terminal such that this other side be negative, then this other side will be the positive terminal. So what will be the effect of reversing? This one you must draw. This is the first case, then we are now reversing. If you don't draw, then you use the rule, you might not get the answer to say here. You will miss something to say here. So we must apply the rule. Then we note the observation. So sketch when it is reversed, meaning the current will be facing, the direction of current will be from Y. The direction of current will be from Y to X. That is the second finger will be facing towards X. You can use a diagram. You can use the diagram and the fingers. You can use the fingers to determine the diagram. So the second finger will be pointing the direction X because the current is flowing from Y to X. We would have already interchanged this one. This one will be the North Pole. This one will be the South Pole, meaning the first finger will point upwards because this one will be the North Pole, that one will be the South Pole. And the direction of the motion of force will automatically be, the thumb will be pointing this direction. From the conductor, the thumb will be pointing to the right, meaning there will be no effect in interchanging, in reversing. There will be no effect in reversing the magnetic field and the direction of current. State factors by which the force XY can be increased. State factors by which XY can be increased. State factors by which the force on XY can be increased. State the factors by which the force on XY can be increased. We know that force increases with the increase in current. And when current increases, the field, the magnetic field strength also becomes stronger. So the force it will increase with increase in current. So we have to increase current, which will also result to a stronger magnetic field strength. Number two, the force will increase with increase in length of the conductor in the magnetic fields. So one of them is the length, increasing the length of the conductor. Number two is increasing the size of current or the amount of current. Increasing the amount of current, and increasing the amount of current will therefore increase the field strength. Name an instrument which uses this effect. Name an instrument which uses this effect. Name an instrument which uses this effect. That is the electric motor. The electric motor will use that effect. Let us see the electric motor here. consider this number 4. The diagram below shows a simple electric motor. Name the parts label. You must know the part. You must know all the parts in the motor. You must know all the parts in the motor. You must know all the parts in the motor. So since name the part labeled X1 and X2 as you state their functions. Let us begin by labeling the parts. X1 and X2. X1 and X2. They are the commutators, or what is the other name of this part? X1 and X2. What is the other name? Part X1 and X2. The other name of part X1, X2. Think it's already time. We'll finish with this. What is the name of part X1 and X2? They are the commutators and the carbon brushes. So you use use plural because there are two. Shall continue from that point. See the next class in the next class is starting in the next 20 minutes. Unless you have any question. Jeremy?
I was just requesting whether we could redo the Fleming's left-hand rule in the next lesson.
Okay, Fleming's left-hand rule.
Yes.
Yeah, okay, noted. Enos? Thank you very much for your time.